let's start, all right? Okay, so where are we last time? We talked about AIC and the BIC. We talked about cross-validation last time, and then we talked about AIC, BIC, right? The idea of AIC, BIC is in linear models. We can use AIC, BIC as a sort of approximate criteria to decide which model is the best. Right? So given these four models, for example, we start from a zero model. We start from a null model with no x, all the way to a four model with both x. Okay, calculate the AIC, BIC, see which one is the smallest, and then that model should be the best, right, according to either criteria. The difference between AIC, BIC, both are based on asymptotic theory, and the difference is that BIC penalize larger model heavier, okay, because BIC is log n times p, and AIC is 2p, so log n is larger than 2, typically, when n is large, so BIC tend to select a smaller model out of AIC. So we saw, we already saw an example last time where we just we go from the polynomial model from degree 1 to degree 5, and then we compute the AIC, compute the BIC, see which one is the smallest. Now in this case, both AIC, BIC select the second degree polynomial, which is the one that fits, that looks like, even to our naked eye, looks like it fits the data best, right? Here's the data. Okay, here's the original data, right? We're regressing miles per gallon mpg on horsepower, and so both AIC, BIC select the second degree, the blue line second degree polynomial is the best model in this case. Okay. All right. So let's see what we can do. All right. Suppose now let's take a look at a different data set. Right. We're going to use the credit card balance data set. I think we have already looked at this data set before. So this data set contains a number of variables. The income, so the credit card holders. All right. It contains the income of the person who holds the credit card, the credit rating of the person, how many cards that person already has, age, gender, whether the person is a student, whether the person is married, and also limit, the current credit card limit that person has. All right, so we're going to you can do a lot of things with this number of variables. You can put many things as the y variable and use the other things as the x variable to predict it. Here let's predict the balance. Okay. Suppose I have so that's the null model with no variable whatsoever, right? And then we have y equal to income, so beta 0 plus beta 1 income plus e. That's another model. What else do we have? We have y equal to beta 0 plus beta 1 limit, right? Plus e, okay? And continue, right? Go on and on, right? So we can have all the other variables. We can also have two variables. We can have y equal to beta 1 income plus beta 2 limit, right? Plus e. And of course, in the end, we have the full model. The full model will simply be y as a linear model of all the variables here, right? Okay, all the variable from income to married plus beta 8 married. Okay. All right. So how many models do we have here? Okay, we go from no variable to including all the other eight variables. Suppose we do not have any interaction effects, right? Just including variable, not including variable. How many models do we have here? 2 to the 8th, right? Okay, 8 variables. So we have 2 to the 8th different kind of models. Now I want to pick the best one out of 2 to the 8th different models. Can we do that? 200. That's 256, right? Okay. So we want to pick the best model out of 256. Which one is the best? The way to do it would be to compute, to fit all the models, and then look at their out of sample error. So theoretically, what you want to do is you want to fit all the models, and then look at each model's out of sample error, and then choose the one that with the least amount of, with the smallest out of sample error. Now in reality, we do not have that out of sample error. So what we can do is we can use a training set, and then we can use a validation set, and then we can do cross-validation. Right? Actually, let me one more word on that later. But one way to do it is to use cross-validation to select the best model. But of course, if you don't want to do cross-validation because of this linear model, you can also use AIC, BIC. So we can fit each model, all 256 different models, and then we can compare the AIC, BIC, and see which one is the best. Right? So that's what we're going to do now. In R, there's a very handy sort of a command, regression subsets. So this is called subset regression from the package leaps. So what we're doing is regressing balance on all the other variables, and what this command does is that it will automatically fit all the possible different combinations for you, right? And then tell you what is the best model according to your criteria, right? And at each different combination. So this is the result, and the result shows you that if we want to include all 8 variables, then of course this is the model we get. But if we only want 7 variables, then we should get rid of married. Okay? If we only want 6 variables, then we should get rid of married and the female and the gender, etc. Right? If we only want 2 variables, we should only include income and the rating. That's what this command tells us. Now, the way that does this is by fitting all 260 different models and compute the AIC by default. Okay, the default criteria is AIC, and we choose and pick the smallest AIC for each number of variables. And then, of course, you can compare the AIC of these selected models to see which one is the smallest, and you can pick that one, right? So, so here, right? So we can see that this, according to the AIC, so all CP, the mallow CP is basically AIC number here. If we go from the best one variable model, right? So the one variable model is rating, right? If you go from the best one variable model all the way to the best 8 variable model, we see the AIC start to decrease as we add more variable to it, until what? Until about here, 1, 2, 3, 4, 5, 6, until we include 6 variables. And then the best 7 variable model start to have a larger AIC. Right? Okay? And later. So the best one is the 6 variable one version. According to, right, so let's go back. So the best 6 variable version is here. Right? So this is the 6 variable version. The 2 variable that we should get rid of is married and gender. Okay? Marital status and gender. Now, what about BIC? If we look at BIC, 1, 2, 3, 4, 5, 6. Which one is the 5? No, this one 4. Okay, so the fourth model is the best, right? It's the smallest BIC, which means that BIC give us 4 variables: income, limit, card, and the student and yes or no. Okay, so what student status? So that's the model given by BIC. Okay, so BIC select a smaller model. Okay, let me correct one thing. Right, the way that this program, the way that this function does in R, is that it fits for each different. So let's say, suppose we only want to pick one variable, right? For this one variable, this function will fit. There are how many possibilities? 8 possibilities. If we only have one variable, so this function will fit all 8 variables, 8 different possibilities, and select the one with the highest R square, or select the one with the best fit. So in other words, when we choose the best variables to include in this specification, we only compare R squared. We do not compare AIC, BIC. Now we go to 2 variables. So we can try all the different 2 variable specifications, right? And then we see which one has the highest R square. Again, so that gave us income and the rating. And when doing that, again, we only compare R squared. We don't compare AIC, BIC. The reason why is because there's no need to compare AIC, BIC if we fix the number of variables, right? Because AIC, BIC only penalize the number of variables. Okay, people remember? So AIC, BIC only penalize the number of variables. The P is the dimension of X. So if we fix the dimension of x, let's say 2 variables. I just want 2 variables, or I just want 3 variables. In that case, there's no need using AIC-BIC. Okay, we should just compare R squared. Another way to understand it is that by fixing the amount of the dimension, right, the amount of variables in this model, we are actually fixing the complexity of model. Okay, in linear models. So we have the same complexity, so there's no need to do cross-validation. There's no need for AIC-BIC. All we need is simply to compare the R squared, and it's fine. However, if we want to decide how many variables we want, right? Okay, so we want to decide whether we want 1 variable or 8 variables. Then we are comparing models of different complexity. Now in this case, we need to do either cross-validation or we need to compare AIC-BIC. So according to AIC criteria, we pick 6 variables, and BIC we pick 4 variables because BIC penalizes the number of variables more, right? Okay, so this is the this is the result here. Okay. All right. So as we can see from this example, it should be pretty obvious to you that this way of doing things cannot be applied if the number of variables, if the dimension of x increase more, right? So here we have 8 different variables. We have 256 different combinations that we can try. What if x is equal to 20 or maybe 50? Then we have 2 to the 50 different configurations we should try. If x is 100, right? You can easily imagine that this try all kinds of combinations and pick the one with the best out of sample performance is probably not the best way to do if our x has a higher dimension than just a few number of variables. Right? If x is low dimensional, then we can try this. But as long as x is the dimension is larger, then it's very hard to try this, right? So let's try to find a way to do if we have a high dimension x. Like if x is a larger dimension one. Well, one method is called a forward stepwise. So let's go to. The idea of forward stepwise is very simple. The idea is we cannot really try all different kind of combinations. There's no way to exhaustively search. It takes too long if the dimension of x is large. So let's try a trick, okay, a sort of a convenient way of doing things, which is we'll start from a null model. We start from so now we have x, our x is a high dimensional thing. We can have x1, x2, all the way to xp, okay? So we have many dimensions of x. We will start from a null model, and then we'll say, okay, let's try to pick the best x among these variables to include in my model, right? So I start with a null model, but then I'll say I will go from null model to a model with only 1 variable. So let's say y equal to beta 0 plus beta 1, x plus e, but this x, I call it xj, okay? So this xj is picked from all the available variables. But which xj should I put in? I'm going to pick the one that give me the highest R squared. So I'm going to try this one, right? So I'm going to try all p different x to see which model give me the highest R squared. And suppose that, so let's say p is equal to 100, okay? So 100 different x. I'm just going to try which one give me the best fit. Suppose that's x30, okay? So number 30 is the best, according to this criteria. I'll put number 30 in here. So that's my second step, right? The third step is I will go, all right? From this, I will go to the next step, which is I'm going to include one more variable. All right, so beta 0 plus beta 1 plus x, sorry. So x30 is already, all right? We have already picked x30. So I'm going to remove x30. Okay, x30 gone from the available candidates. I'm going to try to find the next variable. I'm going to call it xj again. I'm going to try to find the next xj that give me the best fit. So I'm going to try x1, x2 again, but this time no x30, right? So we have x29 and x31, okay? Let me try. Now, suppose this time I find x12 give me the best fit. So I put x12 into it, right? And then, of course, the next step, as you guessed it, the next step would be given x30, and given that I already have x12, what additional variable I should put into my model? So I should go one, so this is called a forward stepwise, in terms of we are step by step by step, including more and more variables. When do I stop? When do I stop? Well, I stop until remember when we go from, when we're doing forward stepwise, right? One step, second step, third step, we're increasingly increase the complexity of a model. Okay? So the model becomes more and more and more complex. So when should I stop? Well, remember the out of sample error typically has this U-shaped curve, right? As we increase model complexity, our out of sample error typically go down first and then start to increase. Okay? So as we increase the number of variables, we should expect the same thing here. The out of sample error should first decrease and then start to increase. So when should I stop? I should stop when the out of sample error start to increase. Okay, so when I'm here and if I add one more variable, the out of sample error start to increase, then that's when I should stop. All right. But how do I even know the out of sample error? Like, how do I ever get to the out of sample error? Well, you can do cross-validation, you can do AIC-BIC. Okay. So after each step, right? So one thing I haven't mentioned before previously is that there's a after each step, after I pick the x30, I will do either cross-validation or AIC-BIC to compute the out of sample error of this model. And then I go to the next step. In the next step, I will pick the x variable that give me the highest R squared, the best fit. Okay? And then after that, after I already done with this model, already selected x12 and x30, I'm going to compute its estimated out of sample error using cross-validation or AIC-BIC. So, and then I will continue doing so as long as my out of sample estimate continue to decline. Until when? Until it starts to increase again. Then that's when I stop. So that's called forward stepwise selection algorithm. Okay. Let's see how it works here. Right. To use the forward stepwise algorithm on the banking, on the credit card data, I'm going to first define a null model. The null model is this model. Okay. Right. So this is I don't have any variable here. That's the null model. Also, I define a full model. A full model is basically my y regress on everything, all the x variables in my data set. And then let's start. Okay, let's start doing the forward stepwise using the step function in R. So here's how we do it. First of all, we have a null model. The null model contains only the intercept, nothing else. Okay, no variables. The AIC is, so here we use AIC as a criteria. Right? The AIC is 4905. And the first step is let's pick an x. Let's first pick an x that gives us the best fit. So let's try, okay? Rating, limit, income, student. We try all of them and see which one gives us the best fit. So to see that, we compare the RSS. Okay, the RSS is residual sum of squares, right? Now, the RSS, look at here, which one give me the highest or the lowest RSS, I'm sorry. If you look at that, the rating seems to give me the lowest RSS. Residual sum of squares. So let's select the ratings. Right. So my first model, the first step is go to from only intercept to balance as a function of regress on rating. So rating is the first variable we pick. After picking this rating, our AIC decline from, the AIC is 4905 here, and now the AIC declined from 4905 to 4359. So the AIC has declined. So let me continue, okay? Now I'm going to pick the second variable to include in my model. So again, we try all the other variables, and we look at the RSS, and looks like income. So this is always ranked, okay, from low to high. So income has the lowest RSS here, residual sum of squares here. Let's pick income as our second variable. So now the model becomes balance as a regression, as a model of rating and income. And then you can see that AIC again declines. So we're still good, okay? It's still declining. Let's try one more, right? So now the student becomes the best variable. So let's put student in. After putting student in, our AIC, let me see. Our CIC again declines. So let's go one more, right? Limit is the best. Let's try put limit into it, and AIC still declines. So one more, okay. Let's see, which 36973, yes. So after I put cards into it, AIC is still declining. Do we have more? Yes, I still have more ages in it, okay? All right, finally, okay, so when we put age into it, our AIC declined to 3679. And then you can, and then what we have is, from here it tells you that if you put gender into this model, AIC will actually increase now, okay? So go from 3679 to 3680. And if we marry, then it go from 369 to 3681. So that's when we actually stop. Because if we do any of the remaining variables, the AIC will start to decline. So that's we stop here. And our forward, finally, okay, this is our forward stepwise selection result. We have selected 1, 2, 3, 4, 5, 6. We have selected 6 variables. Okay. We discard the married and the gender, these 2 variables, because if we include them, our AIC will start to increase. All right. Compare this result with the previous result. Remember, previously, we did not do this forward stepwise procedure. We tried all different combinations, right? Okay. We tried all different combinations previously. And then we use AIC as a criteria to pick the best model. Do we get the same result here? The answer is yes. Okay, let's go back to here, right? Here we tried all different combinations. And according to AIC, the best model is the number 6. Okay, 6 variable specification. And for the 6 variable specification, the model is this. The model is income, limit, rating, cards, age, and student. Exactly the same result as the one that we picked using forward stepwise. So in other words, using the forward stepwise algorithm, we have reached exactly the same conclusion, the model selection result, as if we have tried all different models and using AIC to pick. Okay. So in this case, the forward stepwise algorithm has successfully given us the best model without going through all different kind of combinations. The forward stepwise algorithm is a more economical, or if a computationally feasible sort of a approach to save our computing time, so that we don't have to go through all the different combinations. But as in this case, you can see that they reach the same conclusion, the same result. Is this a coincidence, or is forward stepwise algorithm always guaranteed to find the best out of all different combinations? Well, the answer is this is a coincidence. Okay, forward stepwise do not guarantee that we will be able to find the best model out of all different combinations, right? But it is a reasonable, it is a good approach, efficient approach, to try to find a model that is good enough. Okay, it can never guarantee that we'll always find the best among all different combinations, but it's a computationally efficient way of finding a good enough model for our purposes. Okay. All right. You can also try BIC. Okay. Let's say if in the step function, if we specifically say the k is equal to log n, remember in BIC our penalty is log n times p. Okay. So specifically say k equal to log n, then we are doing BIC. The result, I will not show you the step by step, but the result is we have picked, according to using BIC criteria and using the forward stepwise, we have picked 1, 2, 3, 4, 5. We have picked these 5 variables in the end. Is it the same as using BIC to pick among all the available combinations? No. Last time, when we tried all different combinations, the BIC actually only give you 4 different, right? Only give you 4 variables: income, limit, cards, student. So forward stepwise in this case do not give us the same result. All right? Income, limit, cards, student. Income, rating. Income, limit, cards, right? So there's rating is here, right? So rating becomes one more variable that the forward stepwise pick. So in this case, the forward stepwise does not give us the best using BIC criteria among all available combinations. Right? Okay. Now let me go back to cross-validation because I want to say a couple more words on it that last time I was not very totally clear about. Remember when we talk about cross-validation, just some clarification because people ask me questions after the class. Remember that if we can divide our data into 3 parts, okay? So this is training, validation, and a test. Now, let me put test aside. Let me just assume that we have a test data somewhere, okay? We never touch it, we never use it, we only use the test data at the end to assess how good our final hypothesis is. But let me put it aside. Let's talk about training and validation. Now, the process of model selection is that I have a number of different models from H1 to HL. They're all different models. So I use the training data, right, to select hypothesis G1 to GL. And then I use the validation data to find out the best G star that's among G1 to GL. That is the scheme I gave you last time, right? We also talk about cross-validation. So I said, okay, if I do a random split like training and validation like this, then it is unstable. Okay, the result is unstable. To make it more stable and to fully utilize all the data we have, we can do cross-validation. The idea of cross-validation is that I will divide this amount of data, okay? So I call this D. I will divide the D into K different parts, and I will rotate, right? So this is training, this is validation, or this is validation, the other is training, etc. Right? So I rotate K times and average the result. That's cross-validation. So in cross-validation, do we actually have a validation set or not? Well, yes, because every time we use a different validation set. But because cross-validation uses all the data here, typically people will say this is just a training data, okay? We no longer say this is training plus validation data. People just say this is training data. And then we're just doing cross-validation on the training data by dividing into K parts and using one of the validation, right? So when we're doing cross-validation, again, you can think about the data as being divided only into training and a test. We're only doing 2 parts. And then when we fit our model on a training, we are doing cross-validation here. And each time using one of them as validation and try to pick out the best model. All right? And the training will give us this final G star. And this G star, we can test it. We can test this G star, the performance of G star on the T. Okay. So this is one point I want to make. The second point I want to make is oftentimes people will also do this. Forget about cross-validation, all right? Let's come back to this training and validation. Just one random split. No cross-validation, one random split. Now in this case, if I fit all my models, L models on the training data, it produces G1 to GL, and then I fit G1 GL on the validation to pick the G star, okay? The G star is produced by using what? Using is picked by the validation data. Right? The validation tells me which one is the best. Okay, it's G star. What people typically do is after getting this G star, after knowing which one is the best, right? Suppose model, for example, suppose G star is equal to G. We have 10 different models. So suppose G star is the fifth model. Okay, the 5th model is the best. Well, people after knowing this, what people typically do is they will fit H5, the 5th model, on the entire training data again. Because previously the G is produced by this part of training data. But this part of training data is only part of the data. It's not all the data. So the fit is not the best fit we can get. So after we have picked our best model, I will refit the model on the entire training data set just to improve the fit. Okay? And that will give me a slightly different G star as a result. And I'm going to use this test G star on the test data to see how good it is. This is one more step that people typically do. In cross-validation, it means that after cross-validation, it's the same idea. After cross-validation, tell us which model is the best. Say G5 is the best. I'm just going to fit this G5 on, sorry, not G5, I'm going to fit the H5, right, the model, on the entire data again, on the entire training data again, and then use the test data to tell me how good it performs. Okay. All right, so just want to clarify on the cross-validation part. Okay. All right, so we have talked about cross-validation, AIC, BIC. Now, when we have a linear model, we can use AIC, BIC to help us select the best model. But otherwise, cross-validation is this really general technique that we can rely on to give us an estimate of the outer sample error, right? Okay. What is the limitation of AIC, BIC? Well, let's go back to the case of AIC, BIC. Here we see the limitation of AIC, BIC, first of all, AIC, BIC apply to linear models, right? That's not as general as cross-validation. The second problem is for AIC, BIC is that it does not apply when we are in high dimensional case. In statistics, what do we mean by high dimensional? By high dimensional, we mean our P, the amount of variables, right, the dimension of X is actually larger than the number of data points we have. That's called high dimension. So we have 100 data points and our X is 105 dimensional, then that's called a high dimensional case. In high dimension, if we have a linear model but it's high dimensional, meaning the P is actually larger than N, that almost never happens in economics, right? But in other applications it could happen. In such linear model but high dimensional, what happens to AIC BIC is that it doesn't work. Why? Because when our number of data points is smaller than the dimension of X, then we can always perfectly fit every data point. Okay? In other words, our error term our in-sample error becomes 0. When our in-sample error becomes 0, and then we are considering, okay, whether we should include more variables, the AIC BIC doesn't work. Why? Because in that case, the deviance, the likelihood will be almost 1, and then so that doesn't change, but only the P is increasing. So in this case, for AIC, the more variables you have, it will never pick any variable. So for AIC BIC, it will never pick any model that once P is larger than N, it will never pick any model that increases P, because increasing P will always make it worse for AIC BIC. There's no trade-off anymore. The log likelihood will be 1. Okay, once we reach that high dimensional case. All right, so AIC BIC doesn't work in that case. All right. Cross-validation still does. Okay, but more on this later. Now let's talk about another topic. Okay. So let's come back to the basic linear regression and ask this question. Is it the best we can do? Suppose I have y equal to beta 0, let's just say beta prime x. Okay. Now, this is the simplest linear regression model, and the OLS estimate give us beta hat is equal to x prime x inverse x prime y, right? Okay. Now, one thing we know about this beta hat is that this beta hat is unbiased. Now, what do we mean by unbiased? We mean the expectation of this beta hat will be equal to the underlying beta star. The underlying beta star is the best linear fit in the underlying population. The expectation will be the same. Okay. All right. Now, remember in the foundation class, we talk about the bias variance trade-off. The bias variance trade-off can be written as EY given x prime beta, given x prime beta square, right? So this is expected loss function, expected L2 loss, is equal to variance, I would just say V x prime beta plus, so beta is beta hat, okay, this is our fit. So model fit plus the bias of x prime beta hat, but the bias is, we can say, square, right? And plus the variance of E, which is irreducible error. I don't care about this, okay? Let's delete this variance E. Let's focus on variance plus bias, right? Now we know that for the linear regression OLS, if our beta hat is OLS estimate, then this bias goes down to 0. There's no bias. It's unbiased estimate. So that's gone. Okay? So it turns out that for OLS estimate in the linear regression model, our expected loss, L2 loss, would be simply equal to the variance of our estimate. Okay? X prime beta hat, the variance of our fit, in a sense. Okay, and this variance means, if we draw many different data sets out of the underlying population, every time I get a different beta hat, that's where the variance comes from, right? Okay, so is it the best we can do? Now, what do we mean by the best? To answer this question, we have the Gauss-Markov theorem, right? So people are familiar with this theorem. You have all studied this in your econometrics class, okay? So let me just restate it, all right? Under two assumptions. The first assumption is the underlying CEF, the conditional expectation of y given x, is truly linear, okay? The underlying relationship is really linear. The second is homoscedasticity. Under these two conditions, we say the OLS estimator, the beta hat LS means OLS, the OLS estimator is blue, right? That means best linear unbiased estimator. All right. The idea, first of all, let's unpack it. Okay. Linear estimator means any linear function of y. So the beta hat, OLS beta hat, is a linear function of y. Okay. And among all the linear functions of y, estimated y, it is the best unbiased. Meaning what? Meaning it is among unbiased ones, because we could have biased estimate. But among unbiased estimates, this OLS estimate has the smallest variance. In other words, the variance is the smallest, is the minimum variance, if our beta hat is two things, okay? Number one, unbiased. Unbiased, and number two, OLS. Well, actually, it's the same. Right. If beta has OLS, let me just say, if beta has OLS, then among all the unbiased estimates, this OLS has the least amount of variance. Now we know that because it's unbiased, we know that the variance is basically the expected error, right? Our error function, our expected loss. So in other words, the OLS estimate gives us the smallest expected loss. So it is the best, right? But there is a condition to it, which is among unbiased estimates. The OLS estimator is unbiased. Among all the unbiased estimators, this one, the OLS, has the least amount of variance. It's the best. Now here's the question. What if we allow some bias? Okay? Now that depends on what we care about, okay? So if we care about is the expected loss function, right? If we want to minimize the expected loss, L2, then we don't really care about, so in other words, if we do not really care about its biased or unbiased, we just want to minimize the expected loss, L2 loss, then we know that, yes, OLS is among unbiased estimators, OLS is the best. But what if I can increase bias a little bit? Okay, what if I can be biased a little bit? If the trade-off is, by doing that, I can decrease the variance a lot. Is it possible? If it is possible, then I can find something that's even better than OLS, because I can decrease the overall expected L2 loss. Right, let me show you a graph. Right? Suppose this is the true beta. Right? True beta is equal to beta 0. And the variance, this blue curve, is the OLS estimator. The OLS estimator is unbiased. It's centered at 0. And its variance has, this is its variance, right? You can see the variance here. What I can tell you, what the Gauss-Markov theorem says, is that among all the unbiased estimator, so among all the estimator that's centered at 0, this OLS is the best. You cannot beat it. The other estimators all have larger variance. But what if I allow some bias, so that I can have an estimator that behaves like this? That yes, it is biased, it's centered at 2, not 0, but the variance is significantly smaller. So that in the end, it will give me a better expected loss. How about that? Okay, can we do this? And the answer is yes. The answer is yes, we can. In this case, if we're willing to increase a little bit bias, we can, in many cases, decrease the variance a lot. Okay, increase bias, decrease variance, so that in the end we find a better estimator than the OLS estimator. Right. And one of the first methods we're going to introduce today is called ridge regression, and that's exactly what ridge regression does. Ridge regression is not OLS. All right, it increases bias, so it's more biased than the OLS, but it decreases the variance, so that the hope is in the end, our prediction is better. All right. Here is an example, a simulation that suppose we have 50 data points, and then we have a 30-dimensional x, p equal to 30. The true distribution is normal. Y is the normal distribution of x prime beta star. Now the beta star is the true beta. Okay, so the true beta, we have 50 different true beta. There's no intercept, right? 50 different beta. 10 of them is between 0.5 and 1. I call these large coefficients, and the 20 of them are small coefficients in the sense they're relatively smaller. They're between 0 and 0.3. Okay? So we have a bunch of small and some large coefficients here. Now, here's what I can do. Okay, I can use ridge regression. It's also called a shrinkage method, but I will explain it later. Okay, I'll explain it later. But the amount of shrinkage, I will explain what shrinkage means. But here's the prediction error. The true, you can think about the prediction error as the true out of sample error, right? Here's the true out of sample error. Here is how much I'm going to increase my bias. Okay? So if I increase my bias, increase, you can see that the prediction error actually decrease at first, because I'm able to decrease my variance a lot. And finally, of course, variance increase again. So we get the familiar U-shaped curve. Okay. The way that we increase bias here is by when it comes to ridge regression, the way that we increase bias here is we're going to suppress beta. We're going to make beta smaller in magnitude, so it becomes smaller towards 0. Okay. Let's see. All right. So here you can see that we have 20 small beta that are very close to 0, and 10 relatively large. What ridge regression does is I'm going to shrink these beta towards 0, just make them smaller. In doing so, my model will be a little bit biased. I'm going to increase bias, but I'm actually going to decrease variance. Why does this decrease variance? We can do a simple calculation here. All right. So now it turns out that the expected error, or you can say prediction error out of sample error, is y minus again the x prime beta square. Okay. Now what is this expectation over? This expectation is over both x. So we're integrating with respect to x, and also we're integrating with respect to d, the data sets. Because every time we draw a different data set from the underlying population, I get a different beta head. Okay? So we're integrating over both data set and x. So this is approximately equal to, let's only integrate with respect to data set, but let's try to do the integration over x here, okay, within the bracket, and that's basically 1 over n I yi minus xi prime beta hat square. Okay, so this is approximately approximately integrating, taking the mean out of all the x values. I'm doing inside, and then here outside I'm taking expectation with respect to data set, meaning every time I have a different data set and with a different beta hat. All right. But what is this? So this is also square, right? So this is equivalent to 1 over n, okay? Summation I, expectation. So I take the expectation inside of this square, which is basically give us the variance, because it's unbiased, it gives us the variance of xi beta hat that's the same thing. The expectation inside, okay? The expected, this square is basically the variance of xi beta hat. The sum of all the variance, right, in this variance covariance matrix will be simply the trace, okay? The trace of the matrix, trace of the variance of xi beta hat. All right? Okay. Now, there's also sigma square here. The sigma square represents the random irreducible noise in Y. We don't care about, right? So we can disregard the sigma square. Now, the variance of this is basically the variance of x prime x inverse x prime y, because that's the beta, but then we're doing the x here, okay? So there's x times this. We trust my math. Then what here happens is we can take this out, and the variance of y will just be sigma square, because we assume homoscedasticity by the Gauss-Markov theorem. All right. So we basically have taking this 1 over n trace of this thing, of this matrix x prime x inverse x prime sigma square. Okay. But what is this matrix? What is the trace of this matrix? If you're familiar with linear algebra here, this is simply 1 over p here. Okay? Because if x is 1 over p dimensional, if x is p dimensional, this is just p, right? Otherwise, it's 1 over p. If you think about x is p dimensional, let's just write it p, right? Okay. Now, what is all this calculation does, okay, is to basically give you the approximate idea about the variance, about the expected error here. The expected error is roughly, if we satisfy the Gauss-Markov condition, is roughly sigma square over n times p, okay, times p. Which means what? Which means each additional variable that is not equal to 0. The p here is the dimension of x, right? So how many x do we include on model is proportional to the final variance, or to the final predicted error, right? Expected error. So the out of sample error is linearly proportional to the to the number of variables we included in the linear model. Everybody get that? Right. See this formula, okay? What does it mean? It means that suppose I have x1 all the way to xp. We have p potential variables. Okay, I don't have to include all the variables in my model. If I include only if I do not include any variable, right? So I have no variable, but to go from no variable to one variable, how much additional, like how much prediction error I'm adding to it? What is the variance that I'm adding if I include one more variable? Well, according to this calculation, each additional variable you put in the model roughly will increase your variance by this amount, right? Okay. So in other words, to include more variable in your linear model has a cost, which is it increases the variance, or it increases the prediction error of your model. So if you do not have to include it, why include it, right? That's the argument. The only reason you should include a variable in your model is that it decreases the bias. So if it decreases the bias, it's okay to increase the variance a little bit, right? And that's the idea of ridge regression, right? So, which is I'm going to shrink the parameters beta toward 0. If in a sense that if I don't need it, let's get rid of it, okay? And only leaving the things that matter so that our variance do not become too large. So here is the shrinkage effect, right? As we shrink and shrink and shrink, we can. So this is at this end we have the full model. We have all the variables in the model. But by shrinking all the betas towards 0, I can decrease my variance, and then so in the end the prediction error will decrease. However, if I shrink too much, then my bias becomes very large. So we have this familiar U curve. So what is the best point? The best point is here. That that's always familiar, right? So by now you are very familiar with this U curve. So the best point is this point. That is tell us the best amount of shrinkage we should do. Now, of course, I haven't talked about how to do this shrinkage, right? So here is the ridge regression. Before that, let's see this result, okay? Linear regression. I can do linear regression. Linear regression corresponds to no shrinkage. I do not shrink the beta at all. All the betas at the linear regression level, the OLS value, In this case, what is the prediction error or out of sample error? The out of sample error here is 1.633, which includes bias. Okay, the bias is almost 0. It should be 0, but because we're doing numerical simulation, it's not exactly 0. The bias is very small, 0.006. The variance is 0.627. There's also irreducible error in y, which is the variance of e. So altogether, the prediction error is 1.633. If we do ridge regression, and if we locate here, right, this is the optimal amount of shrinkage, then the squared bias becomes much larger. Okay, it goes from almost 0 to 0.077. So the bias is increased. We're increasing the bias. We're not zero bias. We're increasing the bias of model. But look at the variance, right? The variance goes from 0.627 down to 0.4. Is this a worthwhile trade-off? Yes. Okay. In the end, the prediction error is smaller. So if we only care about prediction error, if we only care about minimizing the out-of-sample error, right, minimizing the expected loss, then the ridge regression gives us a better result than the OLS. Okay? And the idea is, like I said, the OLS has the smallest variance among all the unbiased estimators. But we are going to increase bias a little bit in order to really drive down the variance. And in the end, give us a better estimate. Okay. Right, so how to actually do the shrinkage, right? How do we do the shrinkage in ridge regression? Here is how we do it. Now, in OLS, we minimize y minus beta x. But in ridge regression, square expected. But in ridge regression, we minimize not only this, okay, but also this part. We have an additional part, which looks like this. We're minimizing lambda times the sum of beta j squared, where j goes from 1 to p. We have a p-dimensional model that we minimize this. We have this additional part added to the OLS criteria, right? To the L2. So this is y minus xi prime beta square, sum of it. You can think about this is the RSS on the training data, and in addition to minimizing the RSS, we're also minimizing this part. There's a nicer, easier way to write this, which is simply lambda times the L2 norm of beta, right? So this means L2 norm. People know L2 norm, okay? So this is simply L2 norm square. We can write it this way. It's easier to write. All right. What does this part mean? This part. Forget about lambda, right? Forget about lambda. What does this part actually mean? Now remember, what we're doing is we're minimizing, right? So previously, without this part, we're minimizing the RSS. We're minimizing the L2 on the training data. So we're minimizing this distance, right? Okay. But now I'm adding this part, meaning I not only want to minimize this, but also want to make this as small as possible. So by making this part as small as possible, I'm making what? I'm trying to make a beta really, really small, right? It's very that simple, okay? I'm trying to make the size of beta smaller. And that's shrinkage. It's really simple. The idea of shrinkage is I'm going to make beta smaller so that my model has a smaller variance. It's more stable, okay? So the shrinkage estimator in terms of ridge regression is really simple. It's the same idea. I'm just minimizing the same loss function with an additional, what we call a penalty. Okay. Penalty. So this part is called a penalty, meaning this part, the larger this part, the worse. All right. So we don't want this to happen. We do not want our beta to be large. So I'm going to penalize the size of beta by putting this size of beta into our loss function and minimizing it. So that I want to find the best fit, right? In this part, I'm still trying to find the best fit. However, at the same time, I want my beta to be close to 0 as possible. So we're doing the shrinkage, shrinking to beta to 0, while at the same time trying to find a good fit. That's what ridge regression does. The difference between ridge and OLS, is that OLS doesn't care about the size of beta, but Rich trying to make beta smaller. That's why it's called a shrinkage method. The benefit, like I said, is that by shrinking beta towards 0, our model is more stable. The variance is smaller. The cost is that our beta hat will be biased, not unbiased. But if the trade-off is worthwhile, that we can increase bias but decreasing variance more than we increase bias, then it's the best, right? Okay, so that's the basic idea. But notice that there's also a lambda here. What is this lambda? This lambda is a constant, okay? It can be anything, as long as it's larger than 0. So a lambda can be 0.001, or the lambda can be 1,000 or even 10,000. It can be any constant above 0, or even equal to 0. If lambda equal to 0, we have the OLS. Okay? All right. So it can be anything. But what is the meaning of this lambda? Well, if lambda is really large, what happens? If lambda is really large, then the size of beta will be more important in determining the final loss, right? So in other words, if lambda is larger, then we are penalizing the size of beta more. We're shrinking beta more towards 0. Everybody agrees? Lambda is like how important this part is relative to this part. So if lambda is large, then if lambda is very large, then I don't care how good my model fits. I just want to make beta as small as possible. If lambda is very small, then I don't care about the size of beta. I just want to find a better fit. So as lambda goes towards 0, our beta hat will goes toward OLS. Because when lambda is 0, it's basically OLS. But when lambda is infinity, okay, if lambda is close to infinity, then we don't care about the fit at all. We just want to make all the beta 0 and minimize the loss. Okay. So as we go from 0 to as lambda goes from 0 to infinity, we're shrinking the beta more and more and more. So we're making the model more and more biased, right? Now, but we also decrease the variance. Imagine if the lambda is infinity. Right? So if lambda goes from 0 to infinity. When lambda is 0, we have OLS. Okay. But when lambda is infinity, all the beta hat becomes 0, right? Because you cannot have anything above 0. What happens when all the beta equal to 0? Then our model is what? Our model is y hat equal to 0, right? What is the variance of our model? 0, okay? So as we go from here to here, we're increasing the bias increase, right? Because compared to OLS, because OLS is unbiased. So we're increasing our bias, and we are decreasing the variance, okay? And when it's infinity, the variance is 0. There's no variance when all the beta is 0. And this produces if we add the bias and variance together, that gives us the out-of-sample error, which is this familiar U-curve. So what is the best lambda? The best lambda is the one that gives us the minimum out-of-sample error in here. Okay. So in other words, when we do ridge regression, the most important thing in the whole ridge regression is to try to find the best lambda. Right? You should not tell the model what the lambda is, because we should always try to find the best lambda. The best lambda is the lambda that minimizes the prediction error, okay, by balancing bias versus variance. Right. Okay. Now, there's an alternative way of writing it. Okay. So we just saw that. Well, I just show you here, okay? Instead of me writing everything down on the blackboard, let's just look at the screen because I have it here. Let's look at this formulation. Here we are also minimizing the RSS on the training data. We're minimizing y minus beta x. Okay, on the training data, this is the traditional OLS loss, right? But we're subject to a constraint. The constraint is the norm. The norm of beta is smaller than C. C is the constraint. So in this formulation, we're minimizing this, which is the OLS loss function, but we're making sure that the size of beta, this is the size of beta. Right? We're making sure that the size of beta is within a certain confine, okay, certain limit. If I try to optimize find out the optimal beta hat using this formulation. What does it give me? So people have, you guys know how to do that, right? Taking derivative with respect to beta. If you want to try to find out the best beta hat, then minimize this subject to this constraint. Then what you do is you minimize beta, you take a derivative, plus a Lagrangian constant, right? And adding this part to what you minimize, and taking and making the first order condition equal to 0, right? Which is what? Which is exactly here, right? So this lambda is like your Lagrangian constant, okay? So that's the same thing. In other words, this is one way to write ridge regression. This is another way to write it. Okay? Right, so this is exactly the same way of writing ridge regression. So you can think about ridge regression as having a penalty in your loss function. We can also think about it as the ridge regression as essentially imposing a constraint on the size of beta. They're the same thing. The C actually corresponds to the lambda. Okay? The larger, now when we come to lambda, the larger this lambda is, the more we penalize the beta, right? So the larger lambda corresponds to a smaller C. Okay? We're forcing the beta to be smaller, but that's exactly the same, just one-on-one correspondence. There's no difference between the two formulations. Okay. Now, so this is the basic scheme of ridge regression. And before continuing, just a couple of final points. First of all, for OLS regression, y equal to beta 0 plus beta 1 x plus e, okay? Simple OLS. One question is, does the scale of x matter? Scale means like the size of x, right? So if x become 2x, okay? Just multiply every x value by 2. Does it matter? Does it matter for our prediction of y? It doesn't matter. The only thing it changes is beta 1 becomes beta 1 divided by 2, right? Okay, so that's the only change. Nothing else changes, okay? So in other words, suppose x is wage, right? This is wage. This is some variable I don't know. If x is wage, then this wage can be measured in any kind of currency. It can be measured in RMB. It can be measured in dollar. It can be measured in anything because that only changes the scale. And if it's measured in yen versus measured in dollar, the only thing it changes is the beta. But we're not going to change our prediction of y. Okay, and right, so the beta will be adjusted accordingly. However, when we do ridge regression, if x become 2x, do we end up with beta become beta divided by 2? If we do this very simple thing using ridge regression, x become 2x, do we end up with a half beta so that nothing changes? The answer is no. Why? Because we're not only minimizing this part, we're also minimizing this part. Okay? So in other words, well, let's go from here, right? Suppose x become 1/2 x. Okay. Now in OLS, if x become 1/2 x, beta 1 will automatically become twice the beta 1, right? Here, if x become 1/2 x, do this beta become twice the size? No, because this part, right? When a beta try to become larger, to improve the fit here the beta gets penalized when it becomes larger. So the model will actually force the beta to stay very close to 0, right? Force the beta to stay smaller. So in other words, when we decrease the scale of x, the size of beta will increase, yes, because only by increasing will it improve the fit, but it will not increase to 2 beta because there's a penalty here, right? The penalty here. In the extreme, right? In the extreme, when lambda is infinity, when we change x from sort of 2x to 1, so when we divide x by 2 or multiply x by 2, what happens to beta? Beta doesn't change at all. Beta is always 0, right? When lambda is equal to infinity. So in other words, the scale of x matters in ridge regression. In OLS, the scale doesn't matter. You can multiply x by 100, you can divide x by 100, beta will adjust accordingly. In ridge regression, the scale actually matters. You multiply x by 100, divide x by 100, your beta will not adjust fully, okay, accordingly. So what do? in order to have a consistent estimate, we must always, at least you should, okay, we should always standardize x before doing anything. By standard x, I mean turn every x into a, for example, there are many ways of standardizing, okay? Standardizing has different ways of understanding. But one popular way is to always make the standard deviation of x equal to 1 and the mean equal to 0, okay? So the first step to do ridge regression is for every x, I'm going to minus the mean and divide it by the standard deviation, so that every x has the mean 0 and standard deviation equal to 1. All right? And in doing so, I fix the scale of all the x. So the x scale is always the same. We don't change it. All right? So we can have x measured in dollar or in yen. We'll turn them into the same standardized x first before doing the ridge regression. All right? That's always the first step. The second step is recall that that the way I write it here, I take the beta 0 out. And here is beta 1 to beta p. So beta 0 is the intercept, beta 1 to beta p. And one thing I didn't really say just now is that if you look closely at this formula, the penalty is only on beta 1 to beta p. We're not putting the penalty on beta 0. In other words, we only shrink beta 1 to beta p to 0. We never shrink in beta 0. Why? Why is that case? Because we want to guarantee that in the end, our y hat, the mean value, okay, the mean value of y hat, the value of y hat, we want to make it always equal to the true y. Okay, so in other words, the one way to think about it is suppose this is our data, okay, a bunch of data like this. Now, if we do not do so, one way to think about it is this. All right, so let's try to fit a model of y equal to beta 0. Now I only have a one-dimensional x, okay? So this is x is one-dimensional, but I'm going to have a polynomial model. So beta 1x plus beta 2x squared plus beta 3x to the third. Now if we do more or less on this polynomial model, I can get, very wiggly kind of, model, because, if I include very high terms, okay, all the way to baby beta 5x5, then I get very wiggly, complicated model, right? The variance is very large. So what I can do is I can do ridge regression on this kind of model too. And it will do is it will shrink the beta toward 0. By shrinking beta toward 0, we are making this curve more linear, all right? So, closer to 0. So it's not that wiggly. So we end up with, I shouldn't say make it more 0, but make it more linear. I should say make it, more stable, right? Make it more stable, not so wiggly, because the betas are shrink towards 0, right? But I don't want to shrink the intercept to 0. If I shrink the intercept to 0, I will end up with something like this. It will go down, right? The intercept will go to 0. So that the mean level of my prediction does not match the mean level of the data anymore. The intercept controls the mean level, okay? You can think about it that way. So I should always want the mean level to match the data. That's why I don't shrink the intercept. The intercept is kept the same, but I only shrink, the beta 1, beta 2, beta 3, all the way to beta 5, so that my model becomes more stable, has less variance. That's what we're doing here. So in ridge regression, the beta 0 is kept out. It's not shrinked. Only the beta 1 to beta p is shrinked. Okay. Oh, by the way, when I say something is shrinked, here's the interesting thing. It's actually good English, right? Do we say shrinked or do we say shrunk? If you go to my notes, okay, you can see the first link is shrink, shrank, shrunk, or shrinked. That's a very popular misconception among English language speakers. It turns out that people use shrinked and shrunk all the time, but shrunk is the correct version. But if you read many textbooks, people will say shrinked, or many papers, people will say shrinked instead of shrunk. That's wrong, but I don't care. Okay, so, you can see. All right, So where are we? We said beta 0 is now shrunk. Right, so let's use the better word here. Okay, so what can we do? Well, in practice, what we do is this. We first standardize all the x minus the mean divided by the standard deviation. So we make the mean 0 and standard deviation equal to 1. First step, right? The second step is we take out the beta 0, and the beta 0 hat will always be mean y. Right? So if we standardize x, so this x tilde is the standardized version of our x. So this x tilde has mean 0 and the standard deviation equal to 1. If we do that, then our model becomes y equal to beta 0 plus beta, I'll call it beta tilde, okay? Beta tilde x tilde. How about that? Now in this case, the beta 0, what is the best estimate of the beta 0? The beta 0 estimate will always be equal to y bar. Everybody agree? Because this guy has mean 0, okay? So the best estimate of beta hat will always be mean y bar. In other words, beta 0 controls the level, right? Controls the level. Okay, so I can just get rid of it. Get rid of beta 0 hat, right? So my model now becomes y tilde is equal to beta tilde x tilde. And the y tilde would simply be y minus y hat. So it's called a demeaned y. Right? So y is demeaned minus the mean. Whatever left, we put on the left-hand side. The right-hand side is beta tilde x tilde, where x tilde is the standardized x, okay, not the original x. And then I put this into the ridge regression formula. So what we're doing is our optimal beta tilde is this. Okay, we're minimizing y tilde. Again, y tilde is y minus y bar, y mean. So y tilde minus x tilde beta square, right, plus the lambda times the 2 norm of this beta. Now this beta now, okay, or I can just say beta, right? Instead of beta tilde, I just say beta. This beta now is just all the beta, because we no longer have beta 0. Okay, just all the beta. So I'm just minimizing this part. Right? Okay, so how do we minimize this? Now it turns out that in OLS we minimize this part, right? And we have a closed form solution, meaning we can solve for the formula of the beta hat. There's no need to do numerical optimization. For ridge regression, it turns out that there's no need to do numerical optimization too, because you can solve for beta hat, optimal beta hat. You know, just look at this. It's very easy, right? So let's see. How can I write a? How can I write this thing? Okay, so what I want to do is minimizing. What is that? Y tilde minus x tilde prime beta. So I'm going to put them into a vector form, right? So y tilde is vector form, x tilde is matrix form. So I'm going to say y is the, so y is the vector of all the y tildes minus, I'm going to say x beta. So this x is now a n times p matrix, right? And consisting of all the standardized x, right? So if I want to minimize this square thing, I'm basically minimizing the prime of y minus x beta, right? Okay, same thing. Plus lambda times the 2 norm square of beta, which is simply beta prime beta, okay? So that's what I'm doing. I'm minimizing this thing. So how do I minimize? I take a derivative with respect to beta, set it to 0. So let's take a derivative, right? So the derivative will be 2y minus x beta. Well, there's a prime here because, we take it during matrix derivative. So this one, and then there is a minus x. So we take derivative with respect to beta. So now we have also x here, okay? There's x here, plus the 2 lambda beta prime. Inverse, I'm going to take it equal to 0, which, if you do a little bit, just rearrange, get rid of the 2, get rid of whatever, then what you see is, what you get is lambda beta will simply equal to x prime y minus x prime x beta, and if you move it here, okay, running out of boards, but if we move it to here, then we get our answer. Our answer is, let's move this x prime x to here, then we have x prime x plus lambda I. Now this I is a P times P matrix, identity matrix, because this is a P times P. Okay, X is N times P, so this is P times N, and so this P times CP matrix, right? Plus lambda, but lambda should be times the identity matrix, P times P. This thing beta is equal to X prime Y. So in the end, our beta hat is simply X prime X plus lambda I inverse X prime Y. It looks exactly like the OLS formula. The only difference is now we have this lum plus lambda I here. Okay. So here's the result. Exactly the same as the OLS formula. The only difference now we are plus the lambda here. So immediately you can see that we're shrinking beta. Sorry. Immediately you can see that we're shrinking the beta towards 0. It becomes smaller. As long as lambda is larger than 0, right? This part plus lambda is taking the inverse, because if you think about it, it's divided by plus lambda, right? So we're shrinking the size of beta towards 0, making it smaller. Okay. Now in the special case where this X matrix is orthonormal. By orthonormal we mean, so right now all our X are standardized, right? Our X are all standardized. Mean 0 standard deviation equal to 1. If our X is also independent, every X is independent, there's no correlation, then the X will be orthonormal. Orthonormal means X prime X will simply be the identity matrix. Okay, orthonormal means this is the identity matrix, because so you can check out the definition. But if X prime X is equal to identity matrix, if X is orthonormal, then this has an even better way of writing, an even simpler expression, which is this ridge regression result is simply the OLS result divided by 1 plus lambda. It's very easy, right? You can see that, okay? So this becomes identity matrix, so it's 1 plus lambda. So we essentially have the OLS divided by 1 plus lambda. So as you can see that we're shrinking the OLS estimate toward 0. And how much we shrink is the size of lambda, right? The larger the size of lambda, the more we're shrinking towards 0. Okay, so that's the ridge regression result. All right. So now let's talk about how do we actually pick lambda, right? Because what I'm showing you here is that if I give you a lambda, just give you any value of lambda, I can directly compute the optimal ridge regression result, because we have an analytical solution here. It's really easy, right? Give me lambda, I tell you what beta hat is. But how do we pick the lambda? Well, like I said, we should pick the lambda to minimize the prediction error, right? The out-of-sample error. So lambda should be picked so that we minimize the out-of-sample error, but we need an estimate of out-of-sample error. So how do we do it? Cross validation, okay? All right, so it's the same idea as before. Now lambda here is called a hyperparameter. A hyperparameter is a parameter that we fit not on the training data, but typically on the validation data. All right, so again, imagine that we're dividing our data into a training and a validation. So the process of ridge regression is given each lambda, so training, validation. The process of ridge regression is I give you any lambda, let's fix the value of lambda. Then on the training data, I can find out what is the beta hat. So each lambda will give you a different beta hat. The formula for the beta hat is what we have, is the formula here, right? For each lambda, I have a different beta hat. But what is the optimal value of lambda? Well, let's try to fit them on a validation set, right? The validation set will be in charge of finding out estimate the out-of-sample error of each different lambda values, and then pick the best lambda value. Okay. Now, in practice, we do not do training validation. We do not do this random split for once. We typically do cross validation, in the sense that we have rotating validation and training sets, right? Okay. So here's the procedure. We will the way to fit ridge regression is we'll start with a number of different lambda values. Lambda in theory can be anything, right? But you can start with a sequence of lambda values, right? Lambda can go from 0 to 0.1, 0.2, 0.3. When you program it, you start with a sequence of lambda, 0, 0.1, 0.2, 0.3, all the way maybe to 1,000 or something, right? Depending on the range you're given. So given the sequence of lambda, For every lambda, we fit ridge regression model on the training data, meaning that we use the formula we are just given to compute the beta hat. And then we use cross-validation to find out to estimate the out-of-sample error corresponding to each different lambda values. And then we pick the one with the smallest validation error. Okay, that's called a validation error on the validation side. And then, or cross-validation error, right? And then, typically what people do is they refit. So once we find out the best optimal lambda, we refit the model on the entire training data set using the optimal lambda. So that's the step I just talked about previously, right? So once we pick the best model, we fit on the entire data set again to improve the fit. And that's our final hypothesis. And in order to know how good this final hypothesis is, to know how well it performs, we then use the test data to do that. So that's the sort of training, validation, and test procedure. Okay. All right. Here is the result for the simulation we just had. Right. Let's go back to the simulation. For this simulation, the optimal lambda. So now people understand what is the amount of shrinkage. All right. The amount of shrinkage is. The amount of shrinkage is what? It's simply lambda. So when we talk about shrinkage, like how much lambda shrinkage here is really the size of lambda. As lambda go from 0 to infinity, that we're shrinking more and more. So the optimal lambda is here, somewhere here, right? 5 point or maybe 6 or 7. So at this optimal lambda, what happens is this is the result, okay? So these are the ridge regression estimate. Now we have 30 different parameters, 30 different beta. Linear regression, so these are the true value of beta. These are the linear regression estimate, OLS estimate. And these are the ridge regression estimate. So you can see the ridge regression shrinks all the OLS toward 0. Okay? Shrink everybody towards 0. Right? People can see that? All right. Okay, and we can even plot the bias versus variance to see everything more clearly, right? This is the prediction error or the out-of-sample error. Here is the variance, here is the bias. As we increase our lambda, we are increasing the bias, of course, but we are also decreasing the variance. So the best trade-off is somewhere here, right? But if we do too much, then the variance increases too much, the bias do not decrease. The bias increases too much, the variance stops decreasing much, then we end up with a worse performance as well. So the optimal point will be this here, okay? All right. So it turns out that how well ridge regression performs relative to linear, least square, it turns out it all depends on what? It all depends on the underlying true function, what does it look like? If the in our previous case, in this case, we have 30 different parameters, and 20 of them are very small, close to 0, and 10 of them are relatively large. Now, if we do not shrink, then we'll be spending too much spending. Okay, that's quotation, spending too much variance. Okay, too much effort to fit these small coefficients. And then whenever we're trying to fit very closely unbiased estimate with small coefficients, we're increasing the bias. Increasing the variance of our model. But what if all the coefficients are relatively large? Okay, so let's see. That's our simulation 2. All right. In simulation 2, I'm going to make all the beta coefficients here, rather than making them very close to 0. Now, in this case, ridge regression does not. Okay, in this case, OLS is already pretty good. Okay, right. So if we do ridge regression, we see that we very quickly, run into the smallest optimum in the sense that the bias quickly increase, but the variance do not decrease very much. So the optimal point is actually very close to OLS. Right, so ridge regression performs better if we have a bunch of unimportant, very small effects. Right? So if our model includes many very small important effects, we do ridge regression, it will give us much more stable model, smaller variance, and a more precise prediction than OLS. But if all our so-called effects, all our beta are very large, so that they are all significant and the magnitude is very significant, then doing ridge regression will not improve the results much. Okay, so that's what these simulations show you. All right, before we go, finally, let's look at this credit card. Let's look at the credit card balance example again. Remember, we did the credit card balance. We're doing the forward selection, or comparing all different credit combinations. Here, we're going to do ridge regression, right? In R, we use the GLM net package, and we're regressing balance on everything else. So the way to do it is we first use the model matrix command without the intercept. Get rid of the intercept. Okay? In ridge regression, we don't include the intercept. Get rid of the intercept, make it into x, and then we take the y of the data, and then we use this command glm net, which is the command in this package to do ridge regression. I'm going to regress y on x. I'm not going to explain what this alpha is. We'll talk about this next time. But this lambda is the lambda that we were talking about, okay? So this lambda controls shrinkage. The larger the lambda, the more we shrink. So let's first start with lambda equal to 0.01. That's almost OLS. So in this case, we do not shrink much at all. You can see these are the results. It's very close to 4 OLS, the OLS on the 4 model. But what if we set lambda equal to, okay? I don't even know how much that is, tens of trillions or whatever, right? E to 10. Now, everything here becomes 0. Like all the beta becomes 0. Except what? The intercept. Because we do not shrink the intercept. Okay? Right. So, in this if we use GLM net to fit ridge regression, you can specify lambda. But if you do not specify lambda, what this function does, it will automatically select a number of lambda for you, like a sequence of lambda, and then estimate the ridge regression model for all different lambda values. And then you can use your criteria, you can do cross-validation, or you can use your criteria to pick the best one. Okay? So here typically, here it automatically chooses 100 different lambda values. You can say, the first lambda, we start from this lambda value all the way to the 100. So lambda here actually becomes smaller as we go in the sequence. It generates a sequence of lambda from large to small. The median one is 4,000. So if we look at the median lambda, it is, so this is the result it gives. It's somewhere between the OLS and all 0 specification, right? Okay. So I'll show you how to use cross-validation to pick the best lambda later. But right now, bear with me. Here is the result for the credit card balance ridge regression. As we increase our lambda, so here, look, we are generating 100 different lambda, right? So we can take a look at what happens for all these different lambda values. As we increase lambda, these are the betas. So we have 8 different betas, but some are small, some are large. And you can see that at least the large value beta is very obvious. That as we increase the lambda, they are shrinked towards 0. Okay. We can also, so this plots the coefficients versus lambda. Here we plot the coefficients as on the x-axis, we compare ridge regression beta versus the OLS beta. So let's go from this direction, okay? Here in this direction, we have no shrink. It corresponds to no shrink at all. So the ridge regression is equal to OLS. As we shrink and shrink and shrink, again, ridge regression beta becomes smaller and smaller with respect to OLS, okay, compared to OLS. All right. So here is the cross-validation error. Now, if we do cross-validation for each value of lambda and figure out what is the CV error, then this is the result. As we go from small to large, our CV error starts to very slowly decline, and then start to increase very fast. The optimal lambda here is somewhere here, okay? That's all. At this optimal, so this is the optimal lambda. At this optimal lambda, we are shrinking slightly. The coefficients are shrinking very slightly towards 0. So at least for this example, for the credit card example, it looks like not much shrinkage is needed. Look, for CV error, even if we do not shrink at all, we just use the OLS, our the CV error is actually not much higher than the final result, right? So this is a case where the effects are relatively significant, and the number of variables are very small. We only have 8 different variables. We have a small linear model. It's not unstable at all, right? So remember, the rationale for doing shrinkage methods like ridge regression is that we're worried the OLS may be unstable. Okay, so the variance may be too large in a sense. So we want to decrease the variance. But here we only have 8 variables. The variance is not going to be big anyway. And if the beta also pretty significant, then you do ridge regression, it will show you that the CV error hardly decrease at all. So yes, this is the best. But if you do OLS, that's also good. Okay, so that's the result. And the final beta coefficients here only shrunk very, very slightly. Okay, all right. Okay, so that concludes today's lecture. Next time I'm going to talk about I think lasso. Everybody has heard of it, lasso, right? So maybe people typically tend to know lasso more than ridge, but lasso is a different kind of penalty than ridge. It's very similar to ridge, but it's just different kind of penalty. So we'll talk about that next class. Okay.